College algebra is fundamentally the study of functions. We're going to go over lots of different types of functions. We're going to go over linear functions first, then we're going to go over exponential functions, logarithmic functions, quadratic, general polynomials, and rational functions. But before we go into these specific types of functions, we of course need to know about functions in general. How do we read function notation? What is a function? How do we work with functions? What are we interested in about functions? And that's exactly what we're going to talk about today. As always, feel free to use the timestamps in the description of this video in order to jump to the specific topic that you want to know about. First of all, just what is a function? Well, before we go into a function, we need to talk about what it is we're even talking about, which is relations. Relations are the general type of thing that can relate one thing to another thing. So most commonly, we've been seeing in all of these equations like y equals 2x plus 2. Well, this is a relation. It tells you if I input an x, any given value, let's say a 1, that will output a y. In this case, that y value would be 4. So this tells you 2 outputs 4. So my input is oftentimes my x's, and my output is oftentimes my y's. You can label them differently than just x's and y's, but x's and y's tends to be the notation that we use in 90% of math, and certainly the math that we look at in this class. All of the x's that are allowed, all of the inputs that are allowed is called the domain. So think of this as x's, they are inputs, and all of the y's that are allowed is the range. So this is the y's, this is the outputs. So the domain is the full set of all possible inputs, and the range is the full set of all possible outputs. Other notation you might see in some other classes is an independent variable is sometimes what they call an input, and a dependent variable is sometimes what they call an output. This is mostly the language they use in something like a statistics class. We're pretty much going to use input, output, domain, and range in this class. Let's identify the domain and range of particular relations. And the simplest type of relation I can give you is what's here is called a discrete relation, which just means that it is a finite set that I can literally list out every single point that exists on here. So this is a relation where there are literally 1, 2, 3, 4, 5 points. So whenever I list my domain and range, I'm going to list literally exactly which 5 elements are in my domain and which 5 elements are in my range, or potentially less if there are anything that repeats. So for my domain here, since I'm listing a discrete set of elements, I'm going to use this little curly brace, and I've got 1, 2, 3, 4, and 5 in my domain. That's my full list of domain. For my range, I've got 2, 4, 6, 8, and 10. That's every single input, every single output. Go ahead and try this next one yourself before I go over it. So here our domain is -7, 6, 8, -4, and 50. Our range is 5, 0, 0 repeats, so I'm not going to list them twice, 10, and 102. We care not about all relations per se, but specifically ones that are functions. And what makes a relation a function? A relation is anything where if I have an input that's somehow related to an output, it's somehow connected to an output. But if it's a function, then each input should tell you exactly one output it's going to go to. So here, both Q goes to N, that input has exactly one output. R also goes to N, that input still has exactly one output. If I tell you the input is Q, you know the output is N. If I tell you the output is R, you know the output is N. Or I tell you the input is P, you know the output is X. Tell you the input is Q, you know the output is Y. Tell you the input is R, you know the output is Z. So both of these are functions for that reason. Each input has one output. What's not a function is when I give you a confusing map. If I tell you the input of Q and it can output Y or Z, if you have like a choice between the two, then that is no longer a function. So if it's going to be a function, each input needs one output. So something that would not be a function is if there was like more than one way for me to drive from London Wood to your home. Then that would be, I could input your house and it would output more than one set of directions. Not a function. What would be a function is if there was exactly one path. Only one way you can get there. There's only one answer when I give you an input. And we're going to go over some more examples as well. So, but keep in mind, function means each input has one output. Each input, one output. It's okay if multiple inputs have the same output as each other, but they should only have one output per input. So how do you identify if it's a function? Well, you check that its definition works. So each input should only have one output, each x should only have one y. So let's take a look at this menu example. So this is somewhere where you'd see a function a lot in your day-to-day life. So if I ask you, is price a function of the item? The way this language works is this function of the item, this is telling you the input, and price in this case is the output. So is it the case that if I give you an item, there's only one answer for what the price would be? It is. So that means that yes, it is a function. So each item has only one price. If that was not the case, that would be like an extremely strange store. If I asked for a plain donut and they're like, it'll be some price. That's not how business works, at least here in America. So we're going to have it where each item only has one price. Does it work the other way around? So if I'm asking, is the item a function of the price? Now the price is the input and the item is the output. Does that work? It does not. And specifically, which price is the problem in terms of filling this definition? The $1.99 price, because $1.99 could have two different outputs, so has two outputs. Could be that if you pay $1.99 you got a jelly donut, or maybe you pay $1.99 and got a chocolate donut. I don't know without inquiring further, so the other way around does not work. So let's look at how we use this function notation. Suppose we wanted to say age is predicted by your height. Actually, this should have the other way around. Height, which I will fix in your version, is predicted by your age. That's what I should have said. That was a typo there. That will be fixed. So if we want to say height is predicted by your age, using function notation, your dependent variable, what I am predicting as your height, is predicted by your independent variable, which is your age. So here that means your y is your height and your x is your age. So we're saying height is a function of age. So here h is height is a function of age. We name the function f. You can name it whatever you want. Any sort of variable works. I would encourage you not to label it either an x or a y because that gets super confusing really quickly. But, people use g's, h's, m's, n's, whatever you want. But we're just going to call it f for simplicity. We name the function f and state that the height h is a function of age. So h is equal to f of a. The parentheses here say input a into the function. So that's exactly how you would see it listed here as f of a. So if, for example, I said f of 10, that means input 10 as the a. So let's say there was something slightly more specific for this. Let's say height is equal to 2a plus 3. No idea what this unit is. It's probably not super realistic, but let's say it was. So then if this is the equation and I ask for f of 10, what that's asking me to do is replace everywhere I see the input with this 10. So that's saying 2 times 10 plus 3 to give me 23. That's the idea. We're going to go over this a little bit more with some more concrete examples, but this is the basic idea of how you read this notation. F of A says whatever of is, this is now your input. If you're saying the output is f of A, that means I'm predicting this output. So let's go over this function notation just a wee bit more. So if I have the notation y equals f of x, I'm defining some sort of function f. I read this notation as y is a function of x. That means I predict y by inputting an x. X is your input, also known as an independent variable in some places. Y is your output, also known as a dependent variable. So we oftentimes have seen this as like y equals 3x plus 4. It is identical to write f of x is 3x plus 4. So let's say I wanted you to find f of 2. What would that be asking you to do? That would be asking you to replace everywhere you see an x with a 2. And then you would do 3 times 2 is 6 plus 4 is 10. So you just figured out f of 2 was 10. What if I asked you to find f of negative 1? That means replace the x with a negative 1. 3 times negative 1 is negative 3 plus 4 is 1. So I just figured out that negative 1 maps to 1. I just figured out that positive 2 maps to positive 10. It's just a different way of stating that exact same equation, but now using function notation. And we're going to use this function notation all the time in this class. So the quicker you get used to it, the easier your life will be. Let's go into interpreting this function notation a little bit more. So theoretically, even though most professors will not be so cruel, I could flip-flop where I put the x and y, and in terms of the notation, it matters just where it is. So this y here is still considered an input thanks to its function notation that I have f of y. So a function n, which is my output, n equals f of y, gives the number of police officers n in a town in a year y. What does f of 2005 equal 300 represent? Go ahead and pause the video and see if you can go ahead and create an English sentence yourself. If I'm going to just translate this exactly, that would be that in the year 2005, my input, there were 300 police officers in the town. Police officers being the output. What about the function d equals f of m that gives the number of days d in a month m? So first of all, before I label it, what's considered my input and what's considered my output? My input is m and my output is d. What does f of January equals 31 represent? That represents that in the month of January, there are 31 days. January, the month being my input, the number of days being my output. And that's a great example of something where, yes, each input has one output, but it doesn't work the other way around. If I tell you a month has 31 days, who knows what month it is? There's about, I think, 6 different choices, maybe 5, maybe 7. Don't quote me on that. Not my realm of expertise, but something around there. Regardless, more than one answer. So the other way around is not a function, but yes, inputting the month to output the days is a function. Most of the time, we're not going to be talking about, how many days there are in a month, but a lot of times looking at tables, graphs, equations. So let's talk about how to determine if each of these is a function. So how do you determine if a table represents a function? You will identify the input and output values and check to see if each input value is paired with only one output value. If so, you're good. Your table represents a function. So let's check that. So here I have an input of 2 going to an output of 1, an input of 5 going to an output of 3, an input of 8 going to an output of 6. So for my domain, go ahead and pause the video, see if you can list that yourself. That would be 2, 5, and 8. For my range, also see if you can list that yourself. That's 1, 3, and 6. And is that considered a function? Pause the video and see if you can answer that. Yes, it is. Yes, each element of the domain only has one element in the range. And if you're asked to justify on a test why something's a function, that's all it's asking you to do, is to really emphasize, does this fit the definition of a function? Go ahead and pause the video and see if you can try the next two on your own. So list their domain and range, and then also whether or not they are a function. As a hint, one will be a function and one will not be a function. All right, let's take a look at these. So for this first one, the domain would be -3, 0, and 4. Notice how I'm using these curly brackets rather than parentheses, because if I did something like -3 to 0, that might get confused with interval notation where I'm saying all numbers in between -3 and 0, which is not what I want to say because this table only has 3 elements. For the range, that would just be 5 and 1. 5 repeats, so I don't need to list it twice. And here, each input still just has one output. Even if two of them have the same output, it's still the case that 4 only outputs 5 and -3 only outputs 5. So yes, it's also a function for the same reason. So each element of the domain only has one element in the range. For this next one, now in the domain, if you notice, I've got only just 1 and 5 because 5 repeats. And for the range, that's 0, 2, and 4. So here, does this still fill the definition of a function? It does not, because really this 5, which is really the same element, maps to two different things. So no, there is an element of the domain 5 with more than one element in the range. And I see some students on tests just say there's more than one x. If you're going to say that, that's partially correct. I would just really specify there is an x that has multiple y's, or I misspoke on how students phrase it. Students often say x repeats, which yes is basically the issue. If you notice the x repeats and specifically repeats by mapping to more than one y, then yes, that is an issue. The only thing is, like, I could have listed 5, 2 twice in the table, and that would just be like a really bad table, and that would technically be fine. But as soon as that becomes a different y value, that's where it becomes an issue. So yes, if you notice the x repeats and repeats by having more than one y listed, there is an x with more than one y, there is an input with more than one output, then you're in trouble. It's no longer a function. So just be a little bit careful about that wording if you're ever asked to justify. A visual way to often see if something is a function is the vertical line test, which is really just doing the exact same thing we just did. If, for example, here I've got 1, 2, 3, the element 3, the x3, the input 3, has two different answers here, then it's not a function. That's the idea. So what we do for the vertical line test is we literally sort of either physically or in our mind draw vertical lines everywhere. If the function only passes through the vertical line once, we're good. It is a function. As soon as there is some space where it passes through it twice, it's no longer a function. So something like this sideways parabola, not a function. Something like this ellipse, not a function. Keep in mind, for something like an ellipse, there is a place where it passes the vertical line test. But the fact that there's anywhere where it fails, as soon as you fail once, not a function. And that's just literally what this says. So you just kind of see in your head, if you were to draw a vertical line everywhere, would there be anywhere where it intersects the curve more than once? If so, not a function. So go ahead and pause your video and ask yourself which of these are considered functions. A would be a function. We're good. Everywhere if we draw a vertical line, we only pass once. B is also a function, classically linear. C is not a function because if I draw a vertical line, it's going to pass through more than once. How do we evaluate functions? So remember, we're talking about looking at that function notation where if we input something inside those parentheses, that's what we're being asked to plug into the function for the input. So we want to be familiar with that function notation so that we can quickly evaluate functions. So if this is our function here, and I ask you for h of 4, that's asking you to literally replace everywhere you see this input p with a 4. And I would always show that first step explicitly so that your professor knows that you know how to read that function notation. And then from there, it's order of operations. So I want to do these exponents first. That becomes 16 plus 2 times 4. Then I want to do the multiplication next. 16 plus 8. Then I want to actually add that. So that becomes 24. Go ahead and pause the video and see if you can do this next one yourself. So if I'm asking you to find g of 5, that's asking you everywhere you see the input m, replace it with a 5. In terms of order of operations, what's underneath the square root is like a parenthesis, so it's asking you to do 5 minus 4 first to get you 1, and then the square root of 1 is 1. I could ask you to plug in something spicier, like an algebraic phrase, and it's still the same idea. So if I'm asking you for h of x plus h, that's asking you everywhere you see the input p, replace it with x plus h in parentheses. So instead of a p there, I'm going to replace it with an x plus h all squared. And instead of a p here, I'm going to replace it with an x plus h. Then if you're not asked to simplify, that's technically correct. You might be asked to simplify though. So let's go through what the simplification would look like. To simplify that, you want to FOIL it all out. So I'm just going to go ahead and remind myself that if this is squared, that means I have a copy of it being multiplied by itself. And then I'm going to start doing my distribution. So I do x times x gets me x squared. X times h gets me xh. H times x gets me hx slash xh. I'm going to actually write as xh for my own sanity, but remember h times x is the same thing as x times h. Then h times h gets me h squared. Then I'm going to keep on going with this distribution. So 2 times x gets me 2x. 2 times h gets me 2h. Then I might want to ask myself, are there any like terms? Well, I see an xh and an xh. I can combine those. So that's x squared plus 2xh plus h squared plus 2x plus 2h. And then I would personally call it done. So make sure you check with your professor which format they prefer, because that just might depend person to person. For this next one, same idea. So go ahead and pause the video and see if you can do this yourself. Remember, this just means you want to replace everywhere you see an input with an x plus h in parentheses. Here, because this m isn't being multiplied by anything, the parentheses don't actually do too much. So by the associative property, I can actually kind of just get rid of them. Had there been anything at all being multiplied out front, including a leading negative, which would secretly be -1 though, I would have wanted to make sure to distribute that in. Here I secretly distributed in just a +1, which really didn't do much. And here that's actually done, so that was a lot less simplification. We can also evaluate functions given something else besides an equation, like a table. So if you're doing it from a table, it's asking you to identify based on the table what this is. So here we're not told what g of n is specifically, but remember where we have just an n, that's our input. Where we have a g of n, that's our output. And here this g of 3 notation is saying that n is equal to 3. What is our output? So it's saying our input is equal to 3. What's the output? Well, I go to the table. When the input is 3, the output is 7. No more work needed. This is asking us the other way around for solve when g of n is equal to 6. So here they gave us that the output was 6, and now they want to know what the input is. And this is in a case where there's actually 2 different answers. So n could be 2 or n could be 4. So working the other way around on this table is not a function for that reason. But if I gave you an n, there's only one output, so forwards is still a function. A lot of times we're interested in the domain of functions. So sometimes we can just get that from a graph. Sometimes we have to think a little bit algebraically. So here, for the domain of these functions, well, here if I'm thinking algebraically, if I'm asking myself, what am I allowed to square and then subtract 1 from? That feels like essentially everything. So actually here, there's no issues with the domain. If I were to plug this into a graphing calculator, I would find that it looks somewhat like this. Actually, probably should draw that like a little bit lower down, somewhat like this, but where I've got arrows going off to infinity in both directions, which means that all x's are allowed to be inputted. So here, the domain is just negative infinity to infinity. This function is a similar idea. There's no x values I'm not allowed to plug in. I can do 5 minus a number plus that number cubed for absolutely anything. That's just negative infinity to infinity. And you would similarly find if you plug this into a graphing calculator, it would look something somewhat like this, where your x values are going off to infinity in both directions. If I have, and these rules I should actually emphasize also is true for anything that's a polynomial. That's not a type of function we've formally studied yet, but anytime you just have x to a power, or like an x just chilling by itself in a linear function, that will essentially always be negative infinity to infinity. Actually, that will always be negative infinity to infinity. There's no numbers I'm not allowed to raise to some exponent I'm not allowed to have by themselves. Where we run into something special is a rational function. So a rational function is when I have like 1 over x, when there's x's in the denominator, where there's inputs in the denominator. And specifically, I can never divide by 0. So when you're thinking about the domain of a rational function algebraically, you want to make sure your denominator does not equal 0. And sometimes that requires a little bit of algebra. Sometimes you're able to tell what values that will be at right away. And that will be what you have to think about with domain. So let's take a look at an example here. So here, this is considered a rational function. And I specifically cannot have my denominator equal 0. So in this case, 2 minus x is not allowed to equal 0. It's okay if my numerator is 0. I can do 0 divided by 10. But I can't do 10 divided by 0. So every single time you see an x in the denominator, you should set yourself up a mini equation and ask yourself what values would make that denominator 0. Let me solve for those. Those are the values x cannot equal. This here is like a one-step equation. I want to undo subtracting x by adding x to both sides. So x cannot equal 2. And if I just asked you for any notation, that's technically correct already. So that's saying every single number in the universe except for 2 is allowed. If I want to change that to interval notation on a number line, that would be an open circle on the 2 because I cannot equal 2. But every other number in existence is allowed. So I'm essentially shading in everything except for the 2. And then if I were to actually draw that, that would be negative infinity to 2 union 2 to infinity with a open bracket on the 2, so parenthesis on both of the 2's to indicate I can't equal 2 itself, but I can be any number smaller and any number bigger. Go ahead and try the domain of the next function yourself before we go over it. Here it's a similar idea. You want to note that 2x minus 1 is not allowed to equal 0. Then I want to solve for x this time in a two-step fashion. So first I undo subtraction with addition. So 2x cannot equal 1. Then I undo multiplication with division. So x cannot equal a half. If I wanted any notation, I would be done. If I wanted to translate this to interval notation, I would do an open circle on the half. It's allowed to be any number smaller and any number bigger. So in the order of the number line, that's negative infinity to positive a half. Open parenthesis, union, parenthesis, 1/2 to infinity. Another place I can run into an algebraic issue with the domain of a function is an even root. So by that I mean if I have something like the square root of x, then x has to be bigger than or equal to 0. If I have something like the fourth root of x, same idea, x has to be bigger than or equal to 0. And that's because if I have a negative times a negative, that will equal a positive. And something like the square root of 4, remember, is asking yourself, what number multiplied by itself gives me 4? That would be 2. So we need to make sure that whatever it is we put underneath the square root has to be positive. If I try to ask you for something like the square root of negative 4, well, if I do negative 2 times negative 2, that's also positive 4. So that does not work. We're going to go over negative square roots towards the end of this class. Those are complex numbers. They're imaginary numbers is another way of phrasing it. But that's not something we have to worry about for now. For now, when we're asking about domain, we're asking about real numbers. So if I have an even root, it better be positive. Now, if I asked you for something like the cube root of negative 8, if I stuck a negative under an odd root, well, the cube root of negative 8 is negative 2, because negative 2 times negative 2 gets me 4 times another negative 2 is negative 8. So odd roots, negatives are okay. It's just even roots that you have to worry about. So let's take a look at some of those. So here, I have the square root of 7 minus x. So what I'm going to set up for myself is I want to make sure whatever's underneath that root, in this case 7 minus x, better be bigger than or equal to 0. So I set myself up a little inequality, and then I go ahead and solve. So I want to get x by itself, and I really want to keep my x's to the left with solving linear inequalities because I read left to right. So I'm going to first undo addition with subtraction. 7 minus 7 makes 0. 0 minus 7 makes negative 7. This negative x is secretly negative 1 times x, so then I divide both sides by negative 1. Negative 1 divided by negative 1 is 1. Since I divide by a negative, my inequality needs to flip, and negative 7 divided by negative 1 is positive 7. If I asked for any notation, I would be done. If I want to translate this to interval notation, I've got a closed circle on the 7 because it's allowed to equal 7, and then all numbers smaller than that. So that's negative infinity to 7 with a bracket on the 7. Go and try this next one yourself, and then we'll go over it together. So I have 5 plus 2x has to be bigger than or equal to 0 because what's underneath the root has to be bigger than or equal to 0. Then I just keep on solving. So I want to undo addition and subtraction first, so I subtract 5 from both sides. 2x is greater than or equal to negative 5. Then I want to undo multiplying by positive 2 by dividing by positive 2. Since I'm dividing by a positive, I do not need to flip the inequality. If I ask for any notation, you would be done. If I ask specifically for interval notation, it's helpful to plot this on a number line. All numbers bigger than or equal to, closed circle for the or equal to, negative 5 halves. And then I translate that to being negative 5 halves with a bracket because it's allowed to equal all the way to positive infinity. Do note that with these, had I stuck on like a minus 10 totally outside the square root, that would have no impact on the domain. It would impact my range, which I'm not asking you to find at this point in time, but it would not impact the domain because that negative 10 is not underneath the square root, has no impact on what the underneath the square root evaluates to, so you're good. You just have to, for algebraic domain with a square root, you just need to pay attention to whatever is underneath the root better be bigger than or equal to 0. Algebraic domain with something where there's x's inside the denominator, that denominator better not equal 0. Otherwise, until we learn about logs, you can pretty much assume that if I'm asking you for an algebraic domain, it's negative infinity to infinity for things like polynomials or other things where there's no issues of dividing by 0 or trying to square root a negative. Another way you can find domain is just visually from a graph. So remember, domain is all of the inputs that are allowed. So I'll be looking at all possible inputs by looking at left to right, what x values does the graph touch? And range is all possible outputs. So I'll be looking up and down for all y values the graph touches. So let's look at an example from a graph. So if I'm asking you for the domain of this graph, That's asking you to have tunnel vision and just pay attention left to right. So left to right, I have a lower bound here at -3 that it approaches but doesn't touch because of that open circle. And left to right, I go all the way over to +1, which I do touch because it's got a closed circle. So in terms of domain, that goes from -3 to +1. Notice when I was thinking about the domain, I didn't think at all about what was going on up and down, because all I want to pay attention to is what's going on left to right. For range, I want to do a similar process. So I notice that the range, the furthest up it goes is up here, and even though it only touches over here, it actually crosses here. It actually fully is a closed circle where it fully crosses and touches over here. So here it approaches but doesn't touch, but over here it actually crosses. So we actually would consider it touching that x-axis. It's touching when y equals 0, so we're okay. And then it goes all the way down and stops and actually hits -4. So for my range, when we're talking about up and down, we go from -4 is the lower bound, and that's a bracket because it actually touches it, all the way up to 0 is an upper bound, and that's also a bracket because it actually touches right here. Does not touch over here, that's all right. Since it touches over here, we're good. We're going to consider that 0 a square bracket. And just so that you can actually see the graph. There you go. Go ahead and pause the video and try to think about domain and range of this graph before I go over it. So for domain of this graph, I start here at -4, and then I just keep on going, keep on going, and keep on going. There's an arrow right here, which means it's going off to the positive infinity direction. So for domain, I have a lower bound at -4, which is a square bracket because I actually touch it, all the way up to infinity, which is always a parenthesis because I philosophically never reach infinity. For the range, now I want to have tunnel vision looking just up and down. It does actually touch that x-axis, so it actually touches when y equals 0. And then it just keeps on going up and down. Again, I've got this arrow going off and off and off and off and off. So for the range, my lower bound is 0, because in terms of the y values, that's the lower bound. And then I go all the way up to positive infinity. So this is a good example of like what would be maybe a quick question on a test to see if you understand all of the different notations and things that we can ask about functions. So go ahead and pause the video and try to do this yourself. What are all of these different elements from the graph? So for f of 2, remember that's asking you when x is equal to 2, what is f of x? And f of x is another way of asking for y. It's asking for that output. So I'm going to go over to the input of 2, and that gives me an output of 1. So f of 2 is equal to 1. For the next question, they're asking the other way around. So they're saying f of x, which is the same thing as y, is equal to 4. And they want to know which x values make that true. So I go over to 4 on the y, and I trace over that there are actually 2 different x values that make that true. That would be when x is -1 and when x is 3. If I'm asking about domain, that's asking what values are allowed left to right. And you notice that there are arrows keep on going off in both directions. So here, even though it's happening very slowly, I will eventually go all the way to positive infinity, and I'll eventually go all the way to negative infinity. This is an example of a quadratic. If I were to actually write the equation, it would be something along the lines of x plus 1 all squared. Any sort of number I'm allowed to plug into there, that's totally fine. So the domain is negative infinity to infinity. The range is going to be a little bit different from that because the range certainly has a lower bound. Its lower bound is down here, and then it just keeps on going up. And down here, even though the x value is 1, the y value is actually 0. So the range is that it goes from 0 all the way up to positive infinity. Last but not least, let's talk a little bit about piecewise functions. So this is another special case when we're thinking about domain. So when it's a piecewise function, it tells you, I'm going to have like this formula for these x values for this domain, a different formula for this part of the domain, a different formula for this part of the domain. And let's look at an example for that. So this would be an example of breaking up the domain into these different functions. And the way I would personally approach this is basically make a couple of different tables for each function. So first I'll have my f of x is equal to x squared table, and my x values and f of x values. And here it told me the domain was all numbers less than or equal to 1. So I'm going to start my x's listing off at 1, and then I'm going to come up with a few more that are smaller than that. And then I'll just plug those into my function. So f of 1 is asking for 1 squared, which is 1. So I know I have a point at 1, 1. And that's going to have a nice closed circle because it's allowed to equal. I'm going to note that at the end point, that that's a closed circle. If it's asking me to plug in 0, that's 0 squared. That's just 0. Asking me to plug in -1. Well, -1 squared is also +1. If it's asking me to plug in -2, -2 squared is 4. You might be asking yourself, how did I know to plug in these numbers? Well, I knew I could plug in any number less than or equal to 1, and I know I like integers. I like things that aren't fractions, that aren't decimals. So that's why I personally chose to plug in. And then from there, I'm just going to add an arrow and say the pattern keeps on going from there. For the next part, we just have an output of 3, and don't get thrown off by that. That literally means every x value you plug in, output 3. And I'm going to make a similar x and f of x table. And it looks like here, the upper bound is 2 inclusive. And then we can count down, so I've got 1. And here, 1 is my lower bound, but that is an open circle. I'm not including him because he doesn't have an or equal to sign. And this will be a closed circle here. And because it's equal to 3, that just means literally just make the output 3. No more math needed. Whatever x value I plug in that little part is 3. So at 1, 3, I'm going to have an open circle, and at 2, 3, a closed circle. And then I can connect them. For the last part of my graph, I'm going to make another table. So I have f of x is equal to x, and I'm going to list some x and f of x values. Here now I know the lower bound is 2, but that's an open circle since it's not or equal to. Then I could count up maybe 3 and 4. So if f of x is just equal to x, that just means plug in x, secretly multiply by 1, but do no other work. So we've got the point 2, 2, for example. Plug in 3, that's just 3. Plug in 4, that's just 4. So at 2, 2, open circle, 3, 3, closed circle, 4, 4, closed circle, connect them, and draw an arrow to indicate the pattern keeps going. And in general, if you're asked to sketch a piecewise function, this is how I would approach it. I would make a little mini table with x values that are allowed according to their listed domain for each part of the piecewise function. Now, if I asked you for the domain and range of this, that's easiest to tell from the graph. So from the domain, left and right, I've got an arrow going over here, and then it keeps on going. It stops for this piece here, but then picks back up here, so we just keep on going. Stops for this piece here, but then picks up back up here, so we just keep on going. So really, even though we broke up the domain, once I have x is less than or equal to 1, then pick back up all numbers bigger than 1 that's smaller than or equal to 2, then pick back up all numbers bigger than 2, I've actually just listed all numbers between negative infinity and infinity. If you can't see it visually from the graph, you could also translate it from this part of the piecewise function, that if you were to put all this on a number line, all numbers smaller than or equal to 1, then all numbers from 1 to 2, then all numbers bigger than 2. What I just did was I shaded in the entire number line. I just did it in a very complicated way. But eventually all x values are hit by some piece of the graph, so that domain is negative infinity to infinity. For the range, that's where we want to look up and down, and that's easiest to tell from the graph rather than from the function itself. Well, it's all part of the function, but from the equation part of the function, a little bit harder to tell the range. That's easier to tell from the graph. And for range, I can notice it looks like there's a lower bound here, which this part of the graph does hit, and then it just keeps on going up. Because even though it stops here, initially, it does pick back up over here, picks back up over here, and there's really no y values that are skipped. Now, if there was a big jump in the graph, I would want to note those skipped y values, but there is not. So he just keeps on going. So my range's lower bound is 0, and then he keeps on going to positive infinity. For this one, this should have been noted, which will be noted in the version posted online, but these actually have or equal to signs here. So here you want to do a similar idea of making a little mini table for each part of the piecewise function, and that will allow you to see what the graph looks like. If you're feeling comfortable, I would encourage you to pause the video and go and try this yourself. If you feel like you just need one more example for me to walk you through, that's fine. But I would still encourage you to pause as often as you see fit whenever you feel comfortable enough to start filling out the tables yourself. So let's make a few mini tables. So we first got this x cubed part, and that exists for values starting at -1, but since it has no or equal to sign, that will be an open circle. And then it's just everything smaller. So I'm going to, I almost counted bigger. Everything smaller, so we're talking more negative numbers. So I'll do a few numbers more negative than -1. And then we just want to plug it in. So -1 cubed, that's saying -1 times -1 times yet another -1 will end up at -1. Plug in -2, that's asking for -2 cubed, which gets me -8. Plug in -3, that's -3 cubed, so that's -3 times -3 times -3, gives me -27. And then -4 cubed, that's -4 times -4 times -4, gets me -64. You may notice that a lot of these are sort of off the page, and that's okay. So I have -1, -1, and then I already know -2, -8's like way down here, so I'm essentially just going to draw a line that just keeps going super rapidly down with an open circle on that -1, -1 itself. For the second part, don't freak out when there's no x there. Again, that's actually less work because that's saying all of these inputs in between here, the output is just plain old -2. So let's go ahead and note that in a little table. So here, if I've got my xy's, here I'm counting from -1 all the way up to 4. And here it's closed circle on both because we've got an or equal to on both. And all the way down, y is just equal to -2. It's just a straight across horizontal line. So I've got for that whole part, starting at -1, -2, closed circle, closed circle, closed circle, closed circle, closed circle, closed circle, all the way across, just a straight across line. Then for the last piece of my piecewise function, f of x is equal to square root of x. I can again similarly make myself an xy table. Here it starts at 4 and is an open circle. And while in the past we've been just counting by ones, if I'm thinking ahead for a square root, the square root of 5 is just kind of something funky. I can note it, but I know that the next perfect square root is actually going to happen at 9 because square root of 5 is funky, square root of 6 is funky, square root of 7 is funky. So 4, the square root of 4 is just 2. 9, the square root of 9 is just 3. The next even one would be 16. And by even, I mean integer. Square root of 16 is 4. So here, if I'm going to graph it, again, I just want to know the general shape. I would start off at 4, 2 with an open circle. And then I would know 9, 3 is somewhere kind of here off the page, way over there. So I'm just going to have it very, very slowly increasing from there and indicate that with a nice, beautiful arrow. Now let's talk about the domain and range of this. So for the domain, if you notice left to right, we're talking about all numbers smaller than -1. Then we pick back up at all numbers from 1 to 4. Then we pick back up with all numbers greater than 4. So are there any x values we skipped over? There are not actually. So the domain is just -infinity to infinity. What about the range? Do I have any jumps in the range? I do actually. Right here in between -1 to 2, when we're talking about up and down, there's no part of the graph that's ever going to hit this region here. So that is a discontinuity. It's a jump. That's a jump in the range. So for the range, we want to note that it's all numbers smaller than -1 to all numbers bigger than 2. Because I don't hit any of these numbers in between. It's not physically possible according to my graph. So my range actually does have a jump in it. So you want to always be careful of that. And that's something that's really best told from the graph. I would encourage you to look at your textbook and ask your professor if you have further questions. And best of luck. You're going to do great. I would encourage you to keep on practicing and actively learning.